No, okay, it's being recorded. Hello, guys. Hello, everyone. Hope you are very well, both of you. And today we are going to take the second lesson of quantum machine learning. And as a reminder, a brief reminder, okay, I will try to explain again well, let me do one more thing previous to that, just to do not get disturbed. Awesome. I'm going to share my screen, guys. Please let me know when you can see it. You can look at this. Well, Irais, previous to that, do you know something about machine learning?
Yes.
I mean, well, I mean, it's to say, I'm sorry for that question. It's like I know what Jose knows because Jose attended last session. What I
Mhm.
is to say is, for example, in my case, I know how to develop quantum machine learning, but in fact, I know machine learning, but not a lot, to be honest. Like, it's not my specialization. So, but you already know most of the things. Is to say, when I think about that, is that if I tell you, could you answer me the following question? Is that do you know what is a kernel?
Yes.
Okay, and a future map, you know as well, right?
Yes.
Okay, perfect. Okay, understood. So you know much more machine learning than me, probably.
Well, always depends on the branch you take on when using machine learning, because depending on the on the models you focus on, probably you know more or less about kernels. So
Yeah, I agree with you. Okay, I'm going to do a brief introduction. Okay, what we take care about because we didn't do this too much last week. We were with the main focus of that are the introduction to quantum machine learning and then what we saw the quantum data encoding. Okay. Okay, if you already know most of the things, I'm going to do a rehab, okay, a recap about what we did. And well, as you could see in the PPT and as we saw last week, Jose, in quantum machine learning, if I need to do a summary about that, it should be the summary that I'm going to do is the following, and is that in quantum machine learning, what we have is two, in quantum machine learning, we have two generations. We have the first generation of models that are the ones that have been proved theoretically that there is a quantum advantage against their classical counterparts. They are the most powerful ones and they are the ones that will be implemented in the future. But because of the current state of art of the quantum hardware, of the quantum computers, and the really low quantum volume they have, we cannot perform such models in current quantum computers. Another important fact to keep in mind is that this one they would require also quantum memory, and we currently do not have a quantum memory to do so. So the first generation models are the most important ones, are the most powerful ones to say better, but are not the current quantum machine learning models that are being studied. And what are those ones? Those quantum machine learning models are mainly two, okay? And is the so-called second generation. The second generation is called like that because all of them are birational circuits. They are working in a very similar way to the birational quantum eigensolver. They are working in a very similar way to the birational quantum eigensolver, and they are birational circuits where they have a very few qubits and a very shallow circuit, and they also have an optimization part, a classical part that is regarding optimization. So they are birational because, as we will see now, they are being executed in a quantum computer, but then some parameter is trainable and is going to the classical optimization and going on and so on and going forward, and we have all of this. Okay, and these are the second generation of quantum machine learning models and are the current ones that are being researched. One more important thing is that, as you know, quantum computing is a field where is being well, is being increased a lot. How can I say that is being currently studied, is being currently researched. So a lot of things are still to be discovered, to be done by researchers or by us, by all of us, because we are currently right now quantum developers. So by quantum developers, and this field will grow much because, for example, all what I'm showing you here, I already have some proof of concept with TensorFlow that I like more than Qiskit. The problem is that we chose to use Qiskit as the default provider for the master. So because of this, I have done all of this with Qiskit, but I also like a lot TensorFlow Quantum because they have very good results as well. Okay. And so we have two generations in quantum machine learning models. The first generation is the most powerful, the HHL algorithm, for example, but we cannot use in current quantum computers. And the second generation are variational quantum circuits, variational circuits that are the ones that are currently being implemented in these devices, that are the current quantum computers and the quantum computers we will have in the following 3 years. Okay. So now we have these two. And now into the variational quantum circuits, what is one of is to say what kind of knowledge we may have here and what it needs to keep in mind. Okay, the most important thing, and we saw last week, is the quantum data encoding. Okay, what I mean with that? Can you? Sorry, guys, you can see my screen, correct?
Yes.
Okay, perfect. Thank you very much. In case I didn't know. Maybe I'm just speaking and as it is not necessary, but it will be necessary now. This we saw this last week, Iraiz, Jose, and me, okay, because we were discussing this, and just previous to start talking a lot and a lot and giving you a lot of knowledge and maybe it's a lot of information, etc. The most important thing that you need to keep in mind regarding quantum machine learning is quantum data encoding, meaning the phase, the challenge to translate classical data into quantum data. This is the most important fact and the most important process in quantum machine learning models. This is what it will give you a better or not a better accuracy. And what we did is that, well, as you probably machine learning, because of you say, you know that the future map is this is not a very good picture for a classical future map, but this future, but I just wanted for those people that don't know what to machine. That don't know classical machine learning, how a future map was, and a quantum feature map was in the same way, but basis with different encodings. For example, we have here different examples based in amplitude encoding. This amplitude encoding is the one that is used in the first generation models. The problem is that as of now, create this kind of a state is a very huge computational cost because we need to create an operator and then decompose it into elementary gates, etc. So it is very, very costly, but is the encoding that is mostly used in first generation algorithms. The angle encoding is also very important currently because, for example, one of the outcomes that I had from TensorFlow Quantum is that well, I will tell this later, but this is because with the conclusion. Sorry, guys, but this is very important right now as well. And if I could say something, Iraich, for you, because I told to Jose, but to remind it is that the most important thing for quantum feature map is to one, translate data from classical to quantum data, and this data is going to be available to be analyzed by the model that is going to perform the analysis. And second is that as much difficult, as much complex as the quantum feature map is, the better. Why? Well, this is, for my understanding, this is logical. This I don't know how to say sentido común, but it's like it's something that you keep in mind that is normal. Why? Because if you could if you could perform the quantum feature map in a classical computer, why are we going to use a quantum computer? So it is very important that as much complex as the future quantum feature map is, the better, because a classical computer could not perform the same one to create the kernel, to create the quantum data. Okay, and why saying that, I will come back to, I don't know, seconds ago where I said that this is currently also very important because one of the conclusions that I get from the proof of concepts I developed with TensorFlow Quantum is that uh, the best results we're getting using the three rotation angles gains that are being set in quantum computing, and the area axis, RZ and red y, ry. The three ones is to say in linear, we put the three ones, we do just Rx, Ri, or for example, something like that. And when we put the three ones, were was the most powerful results we get. Okay, and the second one important thing to keep in mind, previous to start with the explanation about, because into the second generation we have two more models that I will explain right now. But regarding quantum feature map, the another one thing to remember is that the ZZ Pauli matrix encoding that has been used from IBM researchers, and is currently demonstrated in a paper that it is also used for other researchers, is the ZZ Pauli matrix encoding. That is the ZZ feature map that Qiskit allows us to use. And this is very used in quantum binary classification because the eigenvalues of the Z Pauli matrix are -1 and +1. And this is a very good way to make a difference, to make a binary classification, because it's -1 in the Bloch sphere and +1 in the Bloch sphere, and it's a good way to classify. Okay, and the Z feature map is contained by rotation angles of Z in Z and entanglement GX gates. Okay, and well, the rest is something, but the most important thing is this. Here you have the conclusion, and the most important thing is the one that I have just said. So just to keep in mind, second generation variational circuits as variational quantum eigensolver. We have different parts that we are going to explain today, and one of the most important thing is the quantum feature map that is belonging to this Jupyter notebook. And quantum feature map, the more important thing, and as much difficult as this is, the better, because a classical computer would not be able to develop such job. And now, just as a reminder, there are into the second generation of machine learning models, there are two different types of models. But I need, sorry, to take the paper. We have two different models. Let me know whether I'm a good professor or not. Jose, could you explain what is this type of model related to? Could you remember that or not?
Yes, is related to the separate the data through vectors, or classify the data through vectors. I remember. I, I think.
Correct. I am going to correct, absolutely. But well, it does not vectors. It's by an hyperplane. Okay,
Yes,
by an
yes.
hyperplane. But yes, it's more or less that. But I would like to do another question if you allow me. And you want to answer, of course. But what is the quantum advantages that is trying to be achieved in this type of model?
I don't remember. Sorry.
Okay, no problem, no problem, Jose. I am not as
You
good as I thought.
you
Tell me,
are
tell
able
me,
to
right?
encode the same information into higher dimensional space, right? So you can maybe
Correct.
separate things that you could not do before.
Yeah, but this is like an analogy about what is being done classically speaking.
Yeah.
Okay. No, what I is to say what I expected, that is not a problem, Jose, because it's absolutely normal. What I expected, the answer was like in second generation quantum machine learning models, we have like two main approaches. The first one is the that is being used with the support vector machine classifier. The first one is called a quantum estimator kernel, a quantum kernel estimation, sorry, because the quantum computer is used to develop the kernel. That the kernel, of course, well, the kernel is the function that calculates the distances of the points into the higher dimensional space. Okay, and of course, but the the main one is that we have two different, in the second generation quantum machine learning models algorithms. We have two different. One is the quantum kernel estimation. That is the one that I'm going to explain right now. And I tried to do last week, but Jose, if you allow me, as you don't remember, we will keep an eye of that because it is important. Okay. And I also say quantum kernel estimation for those quantum support vector machines. Okay. I say this because I like it, but of course it is someone say one thing, the other one. And the other type that is being currently used in quantum machine learning is the variational circuits itself that are the quantum neural networks that we are going to see in the following Jupyter notebook. Okay, and if we have time, I have already uploaded that information regarding. I have already uploaded that information regarding quantum generative adversarial networks. Okay, and if we have time, I will show you. But in case we do not have time here, you already have uploaded the Jupyter notebook in Moodle. Okay. One more thing that I have remember that I'm going to get it down. Okay. Well, let me. Yeah, I will do it later. Is to well, better now. Well, yeah, let me because I want to show you because I didn't thought that, but I'm going to put as well an example of because Qiskit doesn't allow to do so with Quantum One to develop a quantum convolutional neural network, but Google, the TensorFlow Quantum has this feature, has this very simple example, and yes, the quantum convolutional neural network is the quantum neural network, the variational circuit that I have used to develop the use cases that I have done in production. Well, not in production, that is very similar to the real use case. Okay. Yeah, let me just go for my notes. Sorry, guys. Hello, guys. I'm here again. So sorry, but I need my notes because if I don't write something, I always forget it. Sorry, guys. But I'm here again. Okay. So, uh, okay. Quickly, we have in second generation circuits, we have two different ones: the quantum kernel estimation that we are going to see now, and the second one are quantum neural networks that are variational circuits. That is the next Jupyter notebook. Then I will upload the example from the TFQ of quantum convolutional neural networks, and the next one is the quantum generative adversarial neural network. The convolutional one, it's okay. I think it's a good example. It's a very easy example, and it has a lot of applications. And I think you could look at this. The quantum generative adversarial network, you can also look at this, of course, but this is a very complicated, to be honest. Okay, it's to say even for me, it's very complicated. And of course, you have all the information there. You could see everything, but what I mean is that it's like a next level, like advanced. And for me, to be honest, what I really would like from my side that you could learn in this with me is the very basics, of quantum machine learning that I think that it has been said in the documentation I give you. Okay, but for me, it's very important to give you the very basics, how the variational circuits work, etc. You could improve them, etc. And then starting growing up from here with a very good basis, starting going up from here with a very good basis, and be able to develop quantum convolutional neural networks in Qiskit and an hybrid architecture with PyTorch or TensorFlow Quantum. Okay, this is something I wanted also. I wanted as well to introduce in these classes, but only having 6 hours, I thought I didn't realize that I would have all of this time because I should go very very quickly, and I wouldn't let you speak, let you ask about questions. I would rather prefer to let you know a lot of time to questions, to do exercise, etc., and give a very very good basis. Okay, we will try for the following years to try to maybe add more time for that kind of subject, or maybe do a specific subject, etc. But it's okay. So from now, previous to start with that, do you have any questions, guys?
Nope.
Three, two, oh, awesome. Thank you very much, guys. Thank you to answer. Well, I'm going to go a bit quickly here because it's 7 to 20 to 7, and I prefer rather to show you the examples, etc. Okay, and this is what we commented last week as well, Jose, and Lirais, from my point of view, maybe I'm wrong, already knows most of these things. But please remember, interrupt me all the time you want and ask me the questions. We are giving the basis, and for the basis, it's very important to have everything clear. Okay, and so let's go. The quantum kernel estimator, the quantum kernel estimation is being used to develop the kernel of a certain the kernel of a certain machine learning model. As I said at the beginning, you maybe are able to recognize some kernels, but depending on the model, you have one kernel or another. We will see in the following explanation, we will see this example. From that case, what we're going to do is to develop a quantum kernel, okay, to be implemented in a classical support vector machine, in a classical support vector classifier. And just as a quick reminder, what does it do, this model? This model, what it does is that, firstly, we need to apply a feature map to the data as the previous image we have, to a higher dimensional space, to a higher Hilbert quantum space, and there, maybe with the feature map, the data is going to be very much easier classify. So there, what we have is that maybe some data in the plot, and then what we are going to do is to reproduce the kernel, that the kernel is the matrix, or the kernel is the matrix or the function that calculates the distances between the data points. And you could tell me, how is this feasible? Well, if you have the distance between the data points, what you have is that the support vector machine, the support vector classifier, is going to give you an hyperplane very, very well defined. Okay, and an impermanent plane in the 2 dimensionals is a line, and in 3 dimensionals is also a line, but in 3 dimensions, but in 2 dimensions is a line. Okay, and here, any question regarding this knowledge, these concepts, because this is important. If something it hasn't been clear, just let me know right now, please. 3, 2, 1. Okay, I understand. It's clear. Please, if really, I know that I'm very, very, but I'm always bothering you. Let me know your thoughts. Let me know your speaking. I know that, but it's because I like to interact with the people, because this is the first time that I give class online, and I like to speak with the people because I think giving qualitative answers is how the best way when I was a student, I learned. Okay, so taking into account that this concept has been clear, let's go to the quantum kernel estimation. As I told you, the kernel that is over here, the kernel is the function that calculates the distances, the dot product between two different data points in the higher dimensional space. Okay, so this can also be represented by a matrix, and this matrix is what we insert into the super vector classifier. Okay. And how does the quantum kernel estimation model works? Well, first of all, always in all quantum machine learning models, the first of all, what do we do? A quantum feature map. Always. The most important part. The first thing you might do in a quantum machine learning model, in the future for the other ones is the same for the other quantum algorithms is going to be the same. So the first thing for a but for the other quantum algorithms is different because you initialize the circuit, so you apply the Hadamard in all the circuit. But for quantum machine learning models, the first thing is we prepare a quantum feature map to put the training data and calculate the kernel function. Okay. Then, sorry guys. Once we have calculated the quantum feature maps, then it creates like a Kubo function, okay, where the quadratic terms are the distances between different data points and the linear terms are the distances between the points itself, okay? So it creates a Kubo function where is with a classical classifier, with a classical optimizer, sorry, is being optimized to develop the kernel, okay? And once we have this, what we have is the kernel of the function. Then, if we want to test the new data, we need to do the same, but with the maximized kernel from the maximized kernel. Sorry. Okay, and this is how we obtain the kernel and then classify the data with this estimation. And let's see how it does. What was the fact that IBM already give us the quantum kernel function, okay, that let us know to reduce all of this to create by us, program by us manually. It already has this function that encapsulates all of this process and give you the quantum kernel itself, okay. So let's do that. Well, we create the seed. Now what we are going to do is we are going to develop a classification, okay, with the support vector classification. We will see that the quantum kernel function on Qiskit on supervised learning allows us, with supervised learning, allows us to do two things. We will see right now, okay? Well, we develop this. Now, Qiskit already has some data sets that it prepares it, that it gives you, it already does some pre-processing, classically speaking, okay? Like for example, the iris, this is what you need to do in the for the deliverables of quantum machine learning, okay? You need to develop this iris site. And then we have here some data sets that are the very, very common one for classical machine learning, but that Qiskit has already done some pre-classical processing to develop them. Is to say, to feed them for a specific for a specific quantum binary classification model that is, for example, reduce the information from -1 to 1, etc. Okay, I think this is useful. You can look at this as well. Okay, and for our current example, what we are going to develop is that we are going to take advantages of some of these data sets, okay, and we are going to use the ad hoc one, that is random numbers, okay, where we get a training size of 20, a test size of 5, and a gap between the data of 0.3. And for me, in that case, I do a one-off quantification false because for current quantum, well, for the quantum kernel is different. For the quantum neural network is different. We will see that. But because for one hot, you can be used for another one, but not for some for some for some functions. Is to say, what I mean is that in quantum neural network, we will see that we have different functions to custom a quantum neural network variational circuit, and depending on the function, the inputs that it allows us to do the fit analysis are some specific ones, like -1 and +1. If you put an input like, for example, A, B or 0, 1, it will not recognize the new input, and it will give you a very bad score. Okay, that's the reason why, but this is all calculated in the test. Okay, so here what we do is we do a training size 20 and test size 5, where we here have 25 points for each. Okay, where 20 of those are training points and the other 5 are test points. Okay, well, this is an example, level 0 coordinates, etc. We have here coordinated. This is something just to demonstrate what I say, that is, we have here 40 training data, that is 24 level 0 and 24 level 1. And for that case is the same. We have 0 and 1 for the test data. And okay, this is well, this plot over here is exactly the same plot as we have here. To recognize this, remind these 3 points, these 4 points, and here 4 points and 2 points. Okay, remind this 1, 2, 3, and 4. We go there, 3, 4, 4, 2, and 2. Is to say, this is exactly the same plot as we have above. This is exactly the same plot. But why do we see this like this? Because if we do not perform a feature map, a quantum feature map, the way to classify this data is very difficult because we cannot do just one hyperplane, one line in this two-dimensional plot to differentiate the data. We may do a lot of lines to be able to differentiate the data. And this is the reason why we need to perform a quantum feature map to be able to, as in the previous picture that I show you in the quantum data encoding Jupyter Notebook, there is a main reason why we need to perform a quantum feature map to be able to differentiate and classify the data much easily. Okay? This is just the plot. And now what do we do? So now we perform the quantum feature map, and once we have this, that is a ZZ feature map, because as I told you, with that it goes to a higher dimensional where the expectation by is minus 1 and plus 1. It is easy to recognize that, okay? So the feature map, and then we simply, with the quantum instant, this is the way we develop this, as always, we develop the quantum kernel, okay? And now, as I told you previously, that we have two ways to insert, the quantum kernel into the support vector classifier. The two ways are unique kernel matrix, it is regarding for a kernel function, meaning that, well, sorry guys, I need to drink a bit. Meaning that, sorry, meaning that we can insert in the support vector classifier for other supervised, sorry, because I have done some strange thing. For other supervised learning models is the same. We can insert this as a kernel function or calculate the matrices, the kernel matrices separately, and then insert the kernel matrices as the feed points. These are the two ways that we can compute the solution with the classical machine learning models. We can include in the classical machine learning models the function of the kernel, and it will develop the kernel and feed the features with the train and the labels, or we can tell the function, the classical function, that the kernel is already computed, and we put in the feed one the kernel and the labels of the kernel. Okay? So now we are going to develop this with the function. That is the following one. Now it is fitting. Then we can get the score as well. And this is also as previous something that I have done to develop this. Well, I'm going to do this one as well. Okay. And the model validation. Model validation is that we have training data, test data, and validation data. This is some data that the ad hoc dataset allows you to develop some data, and sorry, to develop, just to say, the simple ad hoc dataset allows us to, it gives us, in the same way that it has given the rest of the data, it gives us more data to see how this fits with the algorithm, okay? But we need to wait for that here. Okay, guys, let me. Oh, okay, perfect. Well, we have a score of 1. This is the Qiskit example because of this is so good. In real life, it does not get like this. Okay, but we have the this one. So we have the function, and we have here how it has predicted the data, even with the training features of with the test predict. Okay, and we have a score of 1. And now what we are having here, this is the plots of the matrices that we are going to see, that we are developing, sorry, that we are evaluating, and what we have here is the two kernel matrices. Okay, guys, am I giving you a lot of information, or it's fine from now? Do you have any question?
Is clear for me.
Okay,
Yes, it's clear.
Iraich is good.
Yep.
Perfect. If I am, if some moment maybe you are lost in the class or something, just let me know, please, because I'm not giving you a lot of a lot of questions because I don't want to bother you. I'm always bothering you, but I don't want you to get bored, okay? Because I prefer to be interactive, and if you have any question, just answer me, okay? But yes, as I told you, uh, currently we have two ways in supervised learning. Into unsupervised learning, we could also have the two ways, but as we will see later, Qiskit only allows us to use the precomputed kernel matrix for the unsupervised learning, okay? But well, we will see that. And here what we have is that these tests are the two kernel matrices, the training and the test. And this is how we also get the same answer. We have a score of 1, is to meaning that all have been labeled correctly, but we also have this, okay? And now this is a tip because the way I have chosen this data validation data, and I have do so is with the in the way of the kernel function. So I'm going to evaluate again the ad hoc support vector classifier, and then I will develop the validation input and see how it fits. And well, one thing to keep in mind here as well is the quantum kernel only supports our maximum 3-dimension features, not more. But it only 3-dimension features, but it can classify even with the quantum kernel. You can classify all multi-classes as you prefer. It takes a lot, okay? It has a lot of computational time because this is a simulation, it's not in the real device, but it classifies you even 10 digits, 10 colors, or whatever, okay? But you can only insert 3-dimension features. What it means is that at maximum you can select from a data set 3 variables, okay? 3 qubits. And well, as we could have here, we have a validation input where we have A and B that are two different classes that are corresponding to 0 and 1, and it has been predicted perfect. It also has a score of 1. Okay, so now, is there any question? No? Okay, no problem. You cannot answer. It's okay. But remember, second variational circuits, second generation of quantum machine learning, we have quantum kernel estimator, and into the quantum kernel estimator, it can be used for supervised and unsupervised learning. For supervised learning, how Qiskit is built, we can put the kernel as a function or pre-compute the matrices, the kernel matrices, and introduce them into the classifiers, classical classifier. And now unsupervised learning. With that, as said here, we cannot insert this one as a function. It has some reason because this is not labeled, okay? So we need to pre-compute the kernel matrix and then this insert into an unsupervised learning model. That in that case, we have used the the spectral clustering for that case, but we have also used the agglomerative clustering and the PCA, but the PCA doesn't work properly because I haven't done very good. But for agglomerative clustering, the good fact from here is that you could also make regressions that we are going to see in the quantum neural network one how it does, but it's much more difficult for regression than the kernel matrix, the quantum kernel estimator. Okay? But well, let's go ahead with that. On supervised learning, we are going also to use the ADOC data. The difference is that as this is a As this is a supervised learning, okay, we haven't got label data. All the data is unlabeled. Even if we have the test labels, we haven't got any label data. And secondly, we do not have test size because we uh, is to say we do not have test size because this is supervised learning and all of this is unlabeled. We could introduce them, yes, but it's not recommended because it's not the way how it usually works with real data. So yes, we have this plot that is the same as previously, and this is the same. We're going to do the same as we have done in supervised learning. The main difference is that we do not have label data, so we cannot associate for a feature, for a specific feature, for a specific feature, we cannot associate a specific feature to a certain label, meaning that we can only, for a certain level, we can only pre-compute the kernel matrix for the training data, that is the whole data, and then we will be able to clusterize it with a classical algorithm. Okay, so we perform the same. We develop the quantum kernel always with a feature map. This is the most important part, as this is a binary classification. The feature map works pretty well. Okay, and then now we compute the kernel matrix, and then we pre-compute the kernel matrix and then fit it in the classical algorithm. And here, well, we have used this to score the data because we have the labels. But usually you cannot do that because you do not have it. You just have a label data. So how it works is the best.
And is there any metric we could use in order to see the compactness of the clusters or different dimensions?
I should tell you this one. Is to say, I think most of, or at least all of them, has a way that how they are clustering the data. I know when I is to say uh, when I use these kind of algorithms on unsupervised learning, okay, well, I have mainly done quantum machine learning. So all of them is a very dimensional space, in a very short dimensional space. So what I do is that I plot always the data to see whether it has fitted correctly or not. But the other ways, I always try to, as the clusterization is aggregating the data into different clusters, it is also labeling those clusters. So for me, if I have 3, 4, or 5 dimensional data where it is not easily plot and I need to see that, I always use, of course, the score always. And in case I do not have the score, I try to get the labels of the clusters that the algorithm has done. Does it make sense? Right?
Yeah, so we could basically use classical means to establish if our clustering algorithms is working fine or not.
Absolutely,
Okay.
absolutely. In fact, absolutely, yeah. In fact, you can use the commits here. I have used spectral clustering and then the agglomerative clustering because these are the algorithms that are best fit for this kind of kernel that in quantum we are generating. But in case you could develop a kernel similar for the commits, you could put that. Absolutely, yeah. Okay, well, we have a score of 1, and then for me, when I have worked in data science, like to say in one manner, in the real life, as I always say, because like it's the theory, right? The critical examples, but then we have the real life. For me, in the real life, the metric that I mostly use for that kind of things is the accuracy that I know is normal, but the other one is the deviation. The deviation. Why? Because when there is a lot of deviation, usually there are a lot of problems in the classification. Okay.
Deviation from where? Sorry to ask.
No, no, absolutely. No, 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 absolutely. No, the deviation between between each point. I'm meaning that when you do the training, maybe you get a score of 0.75. Okay, so if you perform the deviation between the points itself, and in the normal distribution, if you see how this deviation is being conducted in the normal distribution, it writes, you are able to see how the data has been pre-processed, and you will do another pre-processing and include the information much better and get a better classification. What I mean with that is that for me, from my understanding in machine learning and in quantum machine learning, the most important fact to get good results is the classical pre-processing. That is the one that I will show you in the next Jupyter notebook.
Okay.
And is the one that has been done into these data sets that QuickSkis allows us as well. Like this this standard mixed mass scalar, this is giving you what is the maximum and less one. The standard scalar is normalizing you the information, etc. This, for my knowledge and my understanding, this is the most important part in machine learning models, because the data quality is very, very important in the real processes, and is very, very important in real processes and in real processes, and it would give you the best accuracy in quantum machine learning and in classical machine learning. From my experience, of course, maybe I'm wrong, but it's the most important. So because of this, I usually use the deviation between each point in the normal distribution. Because like this, I can see whether the feature map that I have selected or that I have done is correctly distributed or not. Because when the deviation is slow, it means that with the normal distribution of the data points, it means that the data points are quite well separated, and because of this, you can use a model that it will distinguish it properly. Okay.
Okay, thank you.
Yeah, absolutely, absolutely. And when here we have the same, we have that, and this is the matrix, etc. Then there is not more things that I could tell you. This is another classical algorithm that we will get the same. Well, I have told you here to do controls and quantum kernel model that classifies the first three components of the data set from Qiskit. The training size would be 8, and this is something whether you would like to do or not. I have done here a lot of more examples. Of course, these examples are not well because I have used different future maps, different. Well, I have used, in fact, this one that with this one is the same like we have done above, but it's different. But it uses the function of kernel. It does not require to pre-compute to compute previously the kernel matrix. It uses as a function, and it does a very good results. Not very good results, very good performance. No results, but we have another one. This is the one from cancer that gives allowed us. For example, I have changing here. I had some problems because I didn't realize at the moment I did, regarding what I told you about the different ways of telling the data how is the data you have. That is one hot encoding, AB 01 or -1 +1, and this is something I did because it was necessary. I wanted to know whether it also distinguishes between AB or not, or only -1 and +1. And now this is fitting the kernel. And when here we here having 3 dimensions. Okay, quantum kernel, when you say 3 variables, is that if you have as here when say 3 variables, is that at maximum you could have 3 dimensions, 3 qubits in the quantum kernel. But of course, all data sets you have, you do a good pre-processing with the PCA, etc. And if you have a data set that is being represented by 4 variables of 20 that it has, for example, you are a bit fucked up. I'm sorry for the word. We're a bit fucked up because quantum kernel only allows us to give you 3 variables. So you may delete one of them or try to compute 2 of them into one. But if you process a good pre-processing, you could introduce here all data sets you have. Well, and now it's fitting. We will see this, and then we will go to and this is some more we have. And I will do so, and we could go to the next Jupyter Notebook as if for variational circuits. Okay. I have done a deliverable over here. That is this one. When still when it is running. Okay. Here it is very simple one. Okay. It's for the iris dataset where training size is 80 and test size is 20. And just 2 and 3 from QCT24 the best accuracy as much as possible, and that's all. And you have here some. I need to get the score and then explain me a bit that, but the same, very similar for what we did in the first subject. Okay. And now looking at this, I think I need to change this deliverable of quantum neural network because I have used the iris dataset as well. And with the quantum neural network, I cannot put you this. I need to put you the iris dataset and delete because the iris dataset is 3. And I cannot give you this one. I need to change it. Because with quantum neural networks, you will see that multi-classification is possible, but it's very difficult. Okay, it is still fitting. We're waiting 1-2 more minutes. Well, in fact, I could. We can be putting like this. Well, guys, I would require, but not now, maybe half an hour or something like that, to do a to do a to do a break. When you want to do that, to do so. Would you like to do it right now, or do you prefer continue and do it later?
Whenever you like.
Okay, guys.
I don't
I
mind.
think we can.
Um,
Thank you, Jose. Thank you, Unites. So I think we can still go further, and maybe we will go deeper. Okay. Okay. So I'm going to start with the next one because I don't want to lose time today. And once I have done all of this, I will see the results of the other way. Okay, of the other case. Well, neural networks. Uh, how much do you know about that? Do you know a lot? Should I explain the basics? What do you prefer?
For my side, you can skip the basics.
Okay, and you, Jose? No
yes,
problem. If I have,
you
okay,
can skip
I
the
can.
basics. No problem.
Okay. So you currently know what is a fit for one neural network, backpropagation, etc. Correct?
Correct.
Yes.
Yes. Okay. Perfect. Thank you, Jose. Thank you, Raj. Perfect. So well, yes, just to keep, yeah, well, the way the connection. Okay, okay. I skip it. So I go directly to the quantum side, quantum neural networks or rational circuits, as I told you. Okay, this is just the basis for those that they didn't know that or they wanted to remark that. Okay. The fact is, well, does not matter. Okay. So I go directly to the quantum side. Yes, perfect. Let's see whether it has finished or not. Okay, it hasn't finished. Okay. But remember, and I told you I'm going to be I'm sorry, but I'm going to bother you about that a lot because I think it's very important just to keep in mind a photo. We have two sides. We have the first generation, the powerful one, and the second generation that are the variational circuits. This one, and into the variational circuits, we can distinguish between two main quantum machine learning models that can be implemented into near-term quantum computers. These devices that are the quantum kernel estimator, that are the one that we have already seen. It works for supervised and supervised learning, and the quantum neural networks that are variational circuits that they work as well for supervised learning and supervised learning. But for unsupervised learning, it is very difficult because it is very important how you translate the parameter to train. Now we will see that. One thing to keep in mind previous to anything, okay, guys, is that variational circuits work very, very similar for the variational quantum eigensolver. Okay? As I told you in quantum machine learning, the most important thing is quantum feature map. Is the most important thing how you encode the data from classical data to the quantum here Hilbert space where you want to work that where you want the data. Okay, and in quantum kernel estimator, we just have a quantum feature map, and then we have the function, and everywhere is the same, because once you have the quantum feature map, what you do is that an optimization of this feature map to create the kernel function. An optimization is it was very similar for here that I want you to explain right now, but you have the quantum feature map, and you have translated the data into the quantum feature map to develop the kernel. You do an optimization. That is the same that we are going to do here. And from that side, this, and what are variational circuits? Well, variational circuits are very similar, as I said several times, to variational quantum Eigen solver, to the VQE algorithm, and they are called quantum neural networks, parameterized circuits, or variational quantum or variational circuits. Okay, and as always in all quantum machine learning models, the first thing to do is prepare the state. That usually is that, or what do we do? A quantum feature map. Okay, the feature map also have fixed parameters, but not the same like the ones that I'm going to explain right now. But the first thing, as always, variational circuits, quantum kernel estimator, quantum feature map. Okay, this is something that I have put here because the quantum feature, because maybe you also would require to do a quantum data encoding, a pre-processing of the quantum data encoding, as maybe as this example, previous to the feature map, as always. Then, once we have the quantum feature map that is common for all quantum machine learning algorithms, in quantum estimator, then we do a classical process. Well, not a classical process because we use a quantum machine, but we use a process that is the quantum kernel to download the kernel. And now here we are not now to compute the same like in the other one. Here we have first quantum feature map. Second, an ansatz. An ansatz is oracle where you have trainable parameters. This is the parameter that is going to be inserted into the classical optimizer when you measure in the quantum computer. Okay, we will go deeper for these understandings, but this is the way. And the last part is an observable of a quantum operator. Okay, so in rational circuits, we always have quantum feature map and ansatz that is the one that contains the trainable parameters. Okay, and lastly, the unobservable that is a quantum operator and is where the expectation value will be measured. Why the expectation value? Well, we have a parameter shift, the so-called parameter shift rule, that this so-called parameter shift rule, what it does is that it performs a quantum gradient by measuring the expectation value. If you measure, if you have the quantum feature map, the ansatz, and then the observable, you have all the circuit, then if you perform the expectation value, that is very similar for what you do in VQE, is that you perform the expectation value, that is this over here, this is the expectation value. If you perform the expectation value for that parameter plus certain type of variables, and minus certain type of variables, this is the formula all variational circuits follows, because it uses the expectation value to get this, because to say this is the expectation value. So you get the expectation value, and by this difference, you could get the gradient of that. And this is the parameter shift rule. And this is the most important part in variational quantum circuits, because you are introducing quantum computing into an hybrid architecture. Okay? Questions over here? Is there any question? Should I repeat something? Because maybe I'm not speaking very well right now. Or is it clear?
Yeah, it's clear.
It's clear.
Okay, awesome. One thing that, for example, in my case, I I had to look at several times is that, for example, this expectation value, I didn't understand why you are putting in the circuit in parallel, not in parallel, in execution, not as well. One following the other. First the quantum feature map, then the ansatz, and then the observable. And why is this expressed theoretically like this? Well, because as you know, in all quantum circuits, you are starting in the state zero, then you apply this operator, and well, in that case, this one over here, this operator, and applying this operator, what it does is that you are constructing a wave function. This operator contains the answers and the quantum feature map. So you have this wave function, and when you finally apply the observable, this is not part of the wave function. So because of this, this is spread like this. Even if the quantum circuit is not like this is spread like this, because this is the wave function. And as you know, the expectation value of a certain observable for a certain wave function is the wave function, like this, wave function, and then in the middle the observable. Okay, so let's go ahead. What have we spoken about, and this is important? The different parts of a rational circuit, that is quantum feature map, ansatz, and observable, and the way how the quantum gradient is computed is by the parameter shift rule that is following this formula over here. And this is the most important thing about variational circuits. So what we have, you have a quantum circuit, you calculate the solution, that the solution will give you the probability and the eigenvalues, and then you multiply everything and you get the expectation value. Once you get the expectation value, you introduce this into a classical optimizer that will uh, that will that will optimize the trainable parameters of the ansatz by a cost function, and then it will go further and so on till in the cost functions a convergence is achieved. Okay, this is cycle. We have a quantum circuit. This is the ansatz, part of the ansatz. You measure the expectation value, you introduce this expectation value in the quantum gradient, you calculate the quantum gradient, and this quantum gradient gives you an answer that is being inserted in the optimizer that will optimize this trainable parameter in order to get a convergence. And this is what I have explained right now is only a quantum lawyer. It's only how a quantum lawyer works. This over here. This is how a quantum lawyer works. But you may also, with PyTorch or TensorFlow, you may also produce an hybrid quantum neural network model where you could also have some some classical lawyers and some quantum lawyers. Okay, and this is something I would like to do to show you, but I couldn't because of the time we have. But this is like next step. Advanced quantum machine learning is to produce hybrid to get the best of both worlds, to get the best to get the best of both worlds in order to get the best, and in order to create a process that is hybrid, it has classical and quantum parts, and you will be able to perform a better classification than only with a quantum node. You need to get the best to get this. Okay, this is another example where this is a quantum lawyer, where you have two lawyers into this quantum lawyer, then you pass to the quantum solution, and finally, if you could also well, this could be also a classical one because this is the classical part of the quantum. But in case you could also like to put a final post-processing neural network, classical neural network, to process the quantum solution to even improve the results of the classification, you could do that. And now we will go with the example, but previous to that, let's see how it is working. Oh, it is fitting. It is still fitting. Okay, so we will wait. So let's go with that. What do we have here? Okay, just let me drink some water. Okay, What do we have here? Well, as we have spoken, we have the variational circuit. Okay, it's one of the circuits that we have in quantum machine learning model, etc. I have repeated this so many times. And inside variational circuits, we have two different forms of classification. We can have classification with supervised learning, or we may have a classification with unsupervised learning as well. We may be able to be using variational circuits as well, or we can do a regression. That is, we will follow it in the following section. Okay, so we are going right now to perform, as I told you, in a QCT has so many different, in fact, has 3 different functions to develop a quantum neural network. And I have given you all of these, and I have given you all of these I have given you all of these examples to see how all of these functions works. For the beginning and for the very basics, I haven't neglected anything. It means that there are 3 functions from Qiskit to develop a neural network. The first one is the one I'm going to show you. It explicitly needs to introduce the quantum feature map, the answers, and the observable into it, and the rest of functions do not require at the first one, to explicitly tell him what is the future map, the answers of the observable, because they have inherent to the function some of the decisions we may have. So because of this, it is not necessary for that. Okay. Just this as an advice. You will look at this. So, but now we're going to develop the full one. So now we are not going to use an IDOC dataset. We will use it later, but we are using random data that we have here with a simple line that can be already used to classify. Okay, and as I told you, we're going to use the upflow quantum neural network classification. That is this one over here. Let's see whether we have the solutions. Not yet. Oof, it's taking too long. Well, here you have more. I wanted to show you more examples, but you can run by yourself. The important thing is the matter. Okay, so now we have here, and we are the function, this one over here. So first of all, as always, what I said, we need quantum feature map, answers on observable. Okay, so quantum feature map, the ZZ feature map, because it's the best for binary classification. That is what we have here. And as I told you, it has a way of that. We have Hadamard. These are rotations in the Z axis. If you decompose it, and this is the C naught gate that is giving entanglement to this one. Okay. After that, what we require? The ansatz. And the ansatz, this is giving us the trainable parameters. In that case, we have 19 trainable parameters that the classical optimizer will develop. Here, we also have parameters, but these parameters are not trainable. The parameters in the quantum feature map are not trainable. The ones that are being trained are in the ansatz. That is this over here. Okay? Of course, you could also look at some future maps that Qiskit allows you. Well, in fact, only JZ future map and Pauli matrices. And the other one, to be honest, Qiskit allows us to use much more ansatz than not future maps. The reason is that ansatz has been used much more time in quantum computing than future map. Future map is something very, very recent, and a lot of people is still being researching on that. And there are a lot of papers that I have written in the documentation for your knowledge. You can read all of this, and this is a lot of information. It is very relevant. And as I told you, this is still being investigated, and maybe another future map better will occur in the near future. Okay, and finally, what do we need to do? We need to develop the observable, and finally join all of these in a common circuit to have all of these expressed in a common circuit. That is this over here. Well, this is the Ansu local. and it have aggruppated everything over here. But well, it is still fine. And I'm going to print this because this is the QCT operator, just to see how it's it. And well, now what we need to do is to compute say what kind of expectation value we want. QCT allows you to have some of them. Then the gradient we require. The natural gradient is also working good here, but I could suggest this one. It gives you much less errors than the other one. And well, as always, the quantum instance. And this is the quantum neural network. Here is where we develop the quantum neural network, okay? Where we need to introduce the operator, that this operator is giving you the quantum feature map, the ansatz, and the observable. Then some input parameters, as I told you, we in the feature map we have some parameters, but they are fixed parameters, and they are not trainable. In fact, you give them some number, and it will be fixed in the whole procedure. So, but the feature maps allows you to give you someone. Then the weight parameters, that are the ones that are trainable, came from the ansatz, as you can see. And then you just need to define the expectation value, the gradient, and the quantum instance. And well, here are some inputs because when you are performing the feed function that is going to be performed here for a neural network classifier, when you perform the feed, what you are really doing, as you know the basics, you are doing the forward and backward constantly till the model weighs the convergence. But Qiskit also allows you to perform these situations independently and step by step. So probably maybe if you would like, this is a forward when you give you an array of one. Okay, this is good because it's what we expected. But maybe you could do a backward and give you some input for the feature map parameters and for the weight parameters, and it would be like a fine tuning. Okay, and it could be a fine tuning for that, as well as quantum weights. You could give here some numbers and you could set them. Okay, and when you perform this, you are giving to the neural network fine tuning, but it is not even necessary because the fit function it works also pretty well as well. Okay, and now what we do here is finally, once we have constructed the whole neural network, quantum neural network, what we do here is finally constructing the fitting and the score, and then see how it fits. Okay, I'm going to do all of this because I think maybe it will require some time, guys. Okay, so if you allow me, I'm going to execute all of this. In that case, I have done this the same one with the same feature map and the same ansatz, but I have chosen different observables because with the identity, this observable is not very good, and as we will see, we are not going to get very good results. But when you use a different observable, uh, taking into account the Z one, because you are using the ZZ feature map, and when you use a more difficult observable, remember, as more difficult the better, because a classical computer won't be able to perform these processes. So as more difficult the better. So if you put another observables, and the best solution I get is with these two ones. If I put X, Y, it wasn't as good because Z is not being introduced, so it's not getting into account into the expectation value for -1 and +1. So it's not better. But if you allow me, I am going to execute all of this. That is the same as above. Okay, it's exactly the same. The only fact is that I am using another observable over here. Okay, I'm using the X and Z. As you can see here, with the identity observable, we are getting very, very bad results because the eigenvalue of the observable identity is just 1. So it does not allow you to compute the expected value and just to have different numbers. You just have 1. So you do not have even 2 different eigenvalues. You just have 1. So it's very bad. It is going to only classify one class, recognize one class, and nothing else. And this is the reason why we have here 0, 25, and it's the same we have here. As you can see, it only produces the class 1, not the class -1. And that we also want the -1 here. Okay. And now, looking at this, okay, it's currently fitting. So let's wait till it finishes. You have any question, guys, over here, or is it more or less clear?
Is
Yes,
more, yes.
yeah, it's clear.
Okay, awesome.
So in this case, if you would use an observable with two eigenvalues and actually two observables, one on each, let's say, string of your qubits, would you be able to encode it in four possible outputs?
No, there are two outputs. There is no one.
Okay.
You have, is to say, I think I have understood your question, Iraita. I'm trying
Yeah.
to answer this more deeply. In case I don't, please repeat me, okay? Just 1 second. This is algebra, okay?
Yeah.
What I mean with that is that we have here two observables where each of the observables independently will have two eigenvalues for each. But as we have done this, that is the sum of Pauli matrices,
Okay.
okay? I'm going to write because it could make it easier.
Yeah, I got it. I was missing the sum of the
Okay.
matrices. So
Okay, you know, is to say, just for you letting you know, okay, perfect. You know that the expectation value is to say the expectation value of the sum of Pauli matrices is the same, and this is a rule that is being used for that case, in fact, and for the VQE. This is like this, you know.
yeah.
So you cannot classify four classes. You can only classify two classes because you still have two expectation values only.
Okay. Thank you.
Okay, absolutely. For variational circuits, it's very difficult to have multi-class, to be honest. You need to do some performance that are not very good. Because of this, I have read the most important researchers I have read about. They always say that quantum kernel estimator is the best approach for second generation circuits rather than variational circuits because variational circuits are good for quantum binary. But as I told you as well, there is a lot of research that has been done, and probably in 1 month or something like that, they found a way to use variational circuits for multi-classes. Okay, but as of now, not that much. And well, here, as you can see, we have obtained a score of 0.9. You can see here 0.9 because for 20 classes, we have incorrectly predicted two. This one and this one. That have been shown here that as for these two, because in that case there are a lot of data points here and very few points here. So if we perform it again, because this is a random distribution, so we can perform it again. But we are going now to use the good observables. For example, this one. We go to the good observables. And maybe we can obtain better results. But yeah, for quantum neural networks is very difficult to multi-classification. For quantum kernel, it is easy. To say in one manner, it's not easy, but it is easy because you are introducing the quantum kernel into a classical. You are introducing the quantum kernel into a classical algorithm, so it's better. In that case, as the quantum algorithm is being set here, it's not that better. let's see. Yeah, here have been. As you can see here, this is an example, guys. Are you there, right? I'm here with the previous example. Here, what I have done is translating this into AB instead of 1 or -1. And as you can see here, it is always predicting the same. B, 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 B. So as we have each data points, we have a score of 0.5, but it is very bad. But the reason of that is that I wanted to show you that in that case that you are predicting with AB, this is not going to predict it correctly. We need to put the data input in the way that it is taking into account the files. That it, in that case is -1 and +1. Okay.
Yep.
Then I have some tips over here that not this one lot, but this is doing, and the one is over here. Well, I have some of them, but it is very important how to put the inputs in that case. Put here this one. Which is like was like something. Well, I will look at this and see. Okay. And now, well, in fact, we get in that case, we get in the other way, we get the 0.9 in the fitting of that. In that case, we are getting a 0.75%. Well, say 0 no, 75% that is corresponding to this one over here. They are wrong, they are not correctly predicted, but the rest of them is correctly predicted. Probably if we use instead of X and Z, we only use Z, it could be go better. Maybe, I don't know, we will see. This is something that you may do in the deliverable. And now, if you allow me, guys, previous to start with this encapsulated formula VQC, we can do a break of 10 minutes or something like that, and I will come back in 10 minutes, okay? Do you
Okay.
agree with that to do an hour break?
Okay.
Okay, yes.
Perfect. Thank you very much. So, see you in 10 minutes, guys. Hello, guys. Are you there? Sorry for the delay.
No worries.
Perfect. Well, let's go ahead and see what we can do now. Well, the specific management. Well, what we have done right here. Oh, sorry, sorry, guys. What we have just done over here, selecting and doing so, is a classification. Okay, and to develop this classification, we have used the upflow and formula. That is this one over here. No, we have above. We have used where we need to define the operator that is inserted by the quantum feature map, the ansatz, and the observable, and then we need to also define the input parameters and the weight parameters. Okay, and what the expectation value, etc. The following formulas that we will use, well, this is going to explain, but there are two more formulas that are the two-layer quantum neural network that we need to use in the example, or at least there are in the examples, and the sequence quantum neural network that we can go, that when we will use it as of now, it will go deeper. And the circuit quantum neural network is a type of, well, the upflow neural network, it only reproduces what you see. Okay, the two-layer quantum neural network is a specific type of quantum of upflow quantum neural network that already already has an input of the ZZ future map for the future map, and you only need to tell him the ansatz that it also get another ansatz that is the real amplitude ansatz, and the observable regarding the Z Pauli matrix. And the circuit QNN, this typical circuit, it is useful because the output of this circuit is not a classification minus +1 or -1. The output of this circuit is in fact what you would like to set up. In a following example, we will see that. But this the output of this circuit can be done in four ways: sparse or density, sparse for taking into account the number of qubits, and density taking into account what is the output you expect. And the other two ways are, or maybe the samples. Imagine you have 10 samples. You to have 10 shots for that. So maybe the output for that is the number of shots that are in each register of the circuit. Imagine you have you are constructing a quantum neural network of 3 qubits. Okay, so 2 up to 3, it's 8, correct? So you will have 8 possible answers. So the circuit and with the samples, you could have what 10 shots you will have. For example, in state 0 we have 2 shots, in state 2 we have 3 shots, so you will have the samples. This one, or maybe you have, instead of the samples and then you compute the probability, you could also have the probability of the samples, the 20%, 50%, etc. And this is the key for that. And with this specific function, you could carry out more complicated models like multi-classification or other things because it gives you the probability of the shots, and you can, apart of that, you can translate the output with a extra lawyer, etc. Well, this is something very, very complicated that I think is next level. If you have any question, please don't have to ask me. But now we will go for the basics, and the basis is that we are going to use the VQC formula, that the VQC uses a circuit QNN with a parity formula. This parity formula is because, remember I have just told you, remember that I have just told you that you could have different ways to obtain a result of the circuit QNN that is not one, +1 or -1. You could also get +1 or -1, but the other ways is that you could have, for example, if you have 3 qubits, okay, you have 8 possibilities. So you can have samples or probabilities. And then what I said is sparse or density. Sparse is that you will have an output of 8 because you have 3 qubits. But if you would like as well, you could define a formula that reduces the dimension of the vector from 8, for example, to 2. And this is the default formula, the default function that circuit QNN uses. Is that the form that is the circuit QNN uses, that is the binary classification. Okay? And this is the one. For example, in my case, I tried to do a third-party classification, and I used another formula because the parity formula does not fix for me for this kind, but we will see it later. So now we are going to use the VQC formula that it requires a one hot. Yeah, it requires. Let me because I always forget. Sorry, I know that usually all the formulas uses -1 and +1, but I know that's it. In that case, as this is using the parity formula, it only reproduces from 0 or 1. That is could be also set in the Whatcom variable, okay? One hot encoding because it's 0 and 1. This one over here, okay? And now we just plot. Well, we are not going to plot the data, but this is the same we have here, okay? But instead of using the whole procedure of defining a future map, the ansatz, and the observable, here we're going to use the VQC that already uses in that case, we can define the feature map and the ansatz, but if we don't put anything, it will use the ZZ feature map and the real amplitude ansatz. And as you can see here, there is not an observable. And why? And it's because the VQC function from Qiskit uses a Z sum of Pauli matrices. Okay, Z, only Z, for 1 qubit, 2 qubits, 3 qubits, 4 qubits, what you want. But we don't use the observable of Z. Okay, but here I have used the Pauli feature map and the real amplitude just to give something. But you could delete this input and we'll use their own functions. Okay, but well, let's go ahead and see how it works. We do this and then we, as always, fit and score and see how the solution is. Okay, guys. Do you have any question right now, or is it clear? I think.
Yeah, it's clear.
It's
Perfect.
clear, yes.
Perfect. What I will try, because it will take longer. Okay. Now I'm going to wait for the answer because I think it's important. Then we will see the quantum neural network regression that I also think is very, very important. Okay. I also think this is very, very important. And one very important fact that is this over here, I will tell you. And in fact, I need to still work on that because it's very complicated, but well, we will see. Then I will show you more examples that I have done here. Okay. For that case, but I have only been able to do the, that case is parity 2. I will show you multi-classification. It is not quite well, to be honest, but well, we will see. And a real use case, okay? I will show you this pre-process classical from the real use case, but we won't be able to develop this because we need to Sorry guys, sorry. We need to, Alberto, we need to improve, no, I don't want even the word in Spanish. It's, we need to search for a way because we cannot execute that. The fit work is taking too long. So we need to do a way to optimize the code. Okay. But this is a real use case that we have developed with TensorFlow Quantum, and I would like to show you. Okay. Some examples, etc. And this. Okay. Okay, we have one score here. Okay, I'm going to explain this. I'm going to load two more things. Okay. Sorry guys, I will not need something because I need to change something. And well, this is like we did. We use 0. And as you can see the feature map, the ansatz, and everything is done. And then we just require to do the fit with the one hot encoding that is important over here. And then we predict it, the X, and as we can see, everything is properly well classified. Probably as this is a binary classification, we are getting very good results because of one thing, and is that we are using Pauli matrices that has two eigenvalues, two different eigenvalues, okay, with the observable Z alone with Z. So the observable of Z, the expectation value, even here we are using for the future map an X and Y, the observer is -1 and +1, that is quite well differentiated for binary classification. Okay? So if you allow me, now I'm going to explain the regression. As all binational circuits, everything is following the same. Quantum feature map, ansatz, and finally the observable. But here in regression is very important how you insert the, is to say you convert the classical data into quantum data, because depending on how you do so, you are going to get bad results and good results or not. In that case, we are going to optimize a sino function. Okay, a sinus function or cosinus function, sorry. A cosinus function. Why I say that? Because we are developing right now a future map that is the RY. And the RY, if we apply, let me, which one was? Let me, because I have already done so here. Sorry guys, but this is important fact I want to highlight here. Here, when putting this feature map, in that case we have done a parameterization from X, because later on in the quantum here in the quantum formula feature map dot parameters, we will give this fixed parameter and the quantum neural network with will set a specific parameter for that. But this parameter is currently the function we want to regress. So in case we would like to regress a logarithmic function, we I'm still encoding that, and all the papers related to that are over here. They are very very useful. I really recommend you in case you have time to look at them. Okay, but in that case, we are encoding the classical data into quantum data by the same function that we want to translate. In other cases, we won't get that result because we are using a cosinus function, for example, to do a polynomial function, and we won't be able to get a good one. And you could tell me, Alberto, but if we do a series of Taylor of the cosinus, we are getting 1 plus x squared over 2 combinatorial plus x up to 4 over 4 combinatorial plus etc. That's correct. So in case you could, for that one, in case you could do a function that is similar to the cosinus, maybe with this future map that we are going over here, that is the rotation over y, maybe you could get good results. I tried and I couldn't. And the reason is that we need to uh, decompose the future map into a expansion of series Taylor series, Taylor series and a Fourier transform, and we need to look at the frequency of the and the frequency of the frequency of the system of the qubit system to obtain what is the best quantum feature map and what is the best function that will go with our regression. I'm sorry, but this is something very complicated. I know a bit about that, but as I told you, you have all the reference over there. If you don't see this reference, just let me know, or in case you do not want to search them over here, just let me know right now, and I can give you in the chat. I can give you the link. All of you want. In case you don't want, etc. It's to say as you prefer. Okay, but this is a very important thing to keep in mind. Okay, so in that case, we cannot perform other quantum feature map but y or rx. If we perform any other feature map, we won't obtain a good result. And the example is the following that I will show you. We want to do the cosinus, okay? The following is the same feature map, ansatz, and observable with z for -1 and +1. Defining the rest is equal, okay? And as we will see here, here I have used x. But it is very important. And one more important thing to do, guys, is that I thought, because in classical learning sometimes it's the same, as much parameters you push to optimize, normally, usually if you have a good computer, the better for do a regression or any other things for me, but I was wrong. In quantum machine learning, not. The parameter, as you increase the number of parameters to optimize, the worst because, not because the function is very complicated, the worst because the the regression and the not the expectation values, or the regression and how these parameters will fit with yours is going to be worse than if you just have one because of the frequency of the qubit system itself. Okay, okay, and as you can see here, it fits pretty well, but because what I show you, we have encoded the data and the feature map in the same way for the function we want to encode. So what happened if we change here? What happened if we change here the future map? Well, let's see what happened. I have done several examples to find out what is this problem like and about. Are you there, guys? I'm boring to you a lot, or it's fine.
No, it's fine.
It's
It's
fine.
fine. For me, to be honest, guys, this is very important. And finally, to end the class, I will give you like one, two, or three tips about that. And one of the most important one is this over here. To do a regression with quantum neural networks with a variational circuit, it's very, very, very important. Very, very, very important to keep in mind how the quantum feature map is going to be done first, and second, to do not give a lot of complexity to this feature map because it will give you another one. Okay. And you can see there is the same cosinus, but what I try, okay, this is good. This is good as well. This is good, but because the future man is only where y, this is the ansatz. Okay, because the ansatz is the trainable parameter. So in the trainable parameters, you can put here 0, 0, 0, and then you just have one, and it does not matter. But in the feature map, as you remember, the parameters are not being trained, so you are giving inputs to that. So because of this is not important because of the frequency of qubits and because you are giving much more parameters. Maybe imagine if you will put one ry and another ry, you are giving two fixed parameters instead of one. Okay, but now it should be here. Here, for example, the feature map is the Fowler feature map that I'm saying for that that is the same like the ZZ feature map because it's only composed but Z Pauli matrices. Okay, so we have this over here, efficient SU, etc. This is all the same. As you could see here, the as well the observable is from Z. So in our mind, would say, okay, -1 +1, binary classification for regression, it could work better. So we will attempt, you see here, very, very bad regression. Very, very bad. Another one here. Well, this fits good because it's the same. Yes. But when you use a feature map that is not like this, it fits very, very bad. This fits good. Pauli to design this is not answer. The answers does not care about that. But as you can see here, why? Because we, for example, in that case, I put the same one but with one, the Rx and Ry. So now what we have is cosinus square and sinus square in the matrix. If you perform the calculus, you will obtain that. So because of this, I'm not getting a good regression here. It is very important to keep this in mind. And for example, like here I use for, and this the same, you see, it is not regressing good because of what I'm saying. Okay, this is something very important. This is something it is required to be working with. And in case, as I told you, you cannot find this reference paper that I'm saying or whatever, just letting me know, okay, and I will give you that. But in that case, of course, because this is example, we obtain a very good accuracy because of that. Okay, and for the quantum regressive Qiskit function is the same. Okay, I'm going to do so, but it is exactly the same. Okay. Very important. If you want, I can let you right now know what is the paper because I have over here all of these to still working. I don't know whether it's here or here. I think it's this one. This is the paper. Our main tool is not representation of such quantum models as Fourier type. Sorry. Fourier type has and series, okay? And this is the frequency. This is the trainable parameter, and this is the frequency of the system. Okay? I'm going to, and it's very present, as you can see. I'm going to write it down in the chat. Okay. Okay, guys. Previous to follow, questions. None? Is it clear? I know maybe this is a lot of information and you need to keep in mind that, but the most important thing is future map. Well, sorry, because I have said questions and I haven't said anything. Yeah, questions?
So depending of the regression function that you choose, you can you can have different results. No, so finally, or at the end of the day, you need to try and test and to test different functions and try to fit the best one, no?
Correct. Well, Jose, absolutely correct. Is to say, as I said at the beginning of the class, the quantum feature map, how you translate the classical data into the quantum data, is the prime factor for a success of the model and getting good results. In case of classification, we haven't got any problems because it have well studied, and ZZ feature map is said to be very good for classification, as well as in TensorFlow Quantum, we develop a very difficult feature map that is Rx, Ry, and Rz, all the combination, because it's very difficult to perform in a classical computer, and it is good. But for regression, it is very difficult to choose what is the quantum feature map correctly do for the regression, and a lot of tests and research needs to be done over here, and not all the feature maps will be able for that. Maybe in 1 year, 2 years, or whatever, some researchers from some university takes a paper where it says, okay, for this type of regression you could require this quantum feature map, for this type of regression you could require for type of feature map. But as of now, anything of that has been studied, only the general form of the paper that I have already shared with you in the chat, and nothing else. But absolutely correctly, Jose, it is very difficult and you need to test all different possibilities to do so.
Okay, thank you.
Absolutely. More questions? Nope. Okay. So I will follow up. That is 20 past 8, and Spain's play in 40 minutes. Okay, guys, perfect. I'm going to go, if you allow me, I'm going to go to the point because all of this kind of data has been already tested, etc. And for example, in that case, it is working properly. In that cases, I'm going to go to the specific one. In that case, if, for example, I'm using the two-layer quantum neural network, that is a specific layer of upflow quantum neural network that it uses the ZZ feature map by itself over here. Well, here I'm using the offlow, but the two-layer is over here as well. Oh no. So here I have used the flow. Well, in the Gaussian, I'm using the two, no, the offlow here as well. Okay, sorry guys. Let's see here. For the Gaussian, I have used the same, but with the two-layer. And as you can see here, you only need to, in the two-layer quantum neural network, introduce the Gaussian dimension, because the two-layer quantum neural network already takes as a feature map the ZZ feature map, as an answer the real amplitudes, and observable the Z observable. And the results are very, very similar. In fact, are even the same. And in the circuit QNN, this is, okay, I'm going to develop this, if you allow me, guys. Okay, and then we'll see that. Yeah. Uh, did you remember that in the circuit QNN I told you different things? The most important one were two. The first one is that the results of the circuit QNN is not -1 or +1 with the classification. The result is the samples of the shots, where is the state that it belongs for the measurement, or the probability to get this state from the shots. And the other thing is that you could get, if you have 3 qubits, a vector output vector of 8 dimensions because you have 3 qubits, or maybe you can use a function that reduces the output of 8 dimensions to the output vector that you would like, and it's going to follow this function over here, that in that case is the parity function, that what it only says is, okay, classify into 0 or 1, nothing else. Nothing else. Okay, and this is here. Sparse, if you put false, is that in that case we are using 1 qubit or 2 qubits. Let me know. Gaussian, okay, Gaussian dimension is 2 because we want 1 qubit used here, or 2 qubits. But now I'm confused. Sorry. Let me know. Let me look at this. Sorry, guys. Vale, no, it's 2 qubits. We are going to use 2 qubits. Okay, but as we are using 2 qubits, we have an output of 4. Okay, So in that case, as we have an output of the circuit coherent, I'm coming back to that because it's okay here. Sorry, we are going to use 2 qubits. So therefore, what we are going to have is an output of 4 possibilities, correct? 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so in the circuit coherent, we introduce the quantum circuit that is the same as previously, introducing the ZZ feature map and the real amplitudes. Here it is not necessary to introduce an observable in the circuit QNL, okay? Only the feature map and the ansatz. Then, well, we define the parameters and the weight parameters. And the other input is that the sparse. Sparse is what I told you. In that case, we have a circuit of 2 qubits. Therefore, we have 4 possibilities, 0, 0, 0, 1, etc. But as we are defining here false, and we have this formula, what we say to the quantum network is, okay, I don't want an output vector of 4 dimensions. What I want is that, okay, use this formula over here and change the output vector from 4 to 2, where these 2 elements of the I vector will tell me what is the higher probability for this point to be the class -1 or the class +1, to be an orange color or to be the blue color. Okay, guys? This is the most important thing for circuit QNL, understanding how the vector, what is the output of that, and how you can use this output. You can use a formula that is the interpret form. How you can use a formula to change the output vector, and in this way you could use 3 qubits, 4 qubits, or whatever, and you could, in this way, you could do multi-classification. We will see an example over here. Of course, it needs to be updated and improved, optimized, everything, but it could be a good example. That is the following one, okay? But let's see how are the results of that. Well, in fact, I think we are not going to wait. I will follow. I think I will follow explaining, and once everything is performed, I will go back. If you agree, of course. If you want, we can wait. Okay, circuit coherent. And how did I use the circuit coherent for multi-classification? Well, I used this for the one dimension. In that case, I said it was 3. And it uses the classification 0, 1, 2 and not a one hot encoding. Okay, for the circuit coherent is 0, 1, 2 and not one hot encoding. Even though this is tested, but of course, I always recommend you to see how the model fits, to see what is using 0, 1, -1, +1, or one hot encoding. In that case, it uses 0, 1, 2 because we are using an interpret. In that case, it's 3. I put 3 because it's the same. It's exactly the same than the other, but it's 3 for this one. Okay, 0, 1, 2. So this is tell me what is the residues of the division between 3, and the residues always only can be 0, 1, or 2 because it's this classification because of the interpret function. That is the parity or what function you would like to use. Okay, so okay, and we do so the same with the one hot encoding to see what the results are. Okay, but always is the same, guys. As you can see, even here, the VQC, the variational quantum classifier, you have a feature map, then you have an ansatz, and then you just feed, etc. Okay, and for this is the loss function that the Covila optimizer optimizes, but it's always the same as I told you. Quantum feature map, ansatz, observable, and go ahead. If you don't see an observable, this is because the Z observable, usually the Z observable has been set to be the default one. Okay. Okay, maybe it will take too long this, but we will see. In that case, if you agree, guys, what I'm going to do is that I'm going to explain the real use case that we have over here. And maybe we cannot see the results. Maybe I will execute this previous to the class of tomorrow and we can comment them. Okay? As you prefer. Is there any question right now?
Nope.
Perfect. Sorry. And thank you very much, guys, because you are all the time answering me. And I really appreciate that. Okay? But perfect. Okay. the real use case that we have developed, I have developed this over here, but I also developed this in TensorFlow Quantum, okay? And I get very, very good results, even 97% of accuracy with the model, with an hybrid model, with an hybrid model. Just with the quantum lawyer, I get 92%. And with the quantum, with an hybrid model, with a pre and post processing, sorry, sorry. Sorry, guys. So sorry. It's summer and I'm like this. Very bad. Well, in that case, the real use case that I'm defining here is fraud detection. How is it belonging? Well, this is belonging that for a certain type of variable, okay, for a certain type, we have certain variables to describe a banking transaction, and the model is to tell you whether this transaction is counterfeit or not. Okay, this is the model. And how we do that? Well, the first and the most important one is feature reduction and distinction data. Is the classical data pre-processing that I always do for that. One important thing to do, guys, is that I have put fear fraud that data set because I have the original one here, but it's too big. It's too big, so I needed to reduce it. So you have an example of this data set, but is reduced to very low rank, and this is what I have unloaded in the model. Okay. But as I told you, let's go ahead with that. I'm not going to execute that because we have too many things here. It takes longer even that. But with pandas, it's working pretty well, but the rest is not working as well as as I prefer, as I would like as I could prefer. But well, we'll see. Well, the number of qubits was set in four number of qubits because, as we will see later on, the data set is explained with four variables. We do a PCA, and this PCA told us that the data set is in the four variables. But this is very similar. The pre-processing that I have done here is very similar what is done in Qiskit for the data sets that they already have. Okay, guys. So let's go ahead. Number of qubits is four, and then what do we do is that we look at the information. Apart from that, what I say to the data frame is, okay, just bring the transactions that are cash out or transfer. That are the ones that are defining a banking transaction. Because for the rest of transactions, you need to clean the database for that, do the data set to obtain the best, to obtain really what you want. The rest of transactions was more like for not business perspective, but more was from technical perspective that they wouldn't be necessary. So then what do we do? So there is a column in that data set that is fraud, zero or not. So this is what we wanted. But we also wanted to delete this because it was not very expressive. And we wanted to delete other variables that were not very similar, etc. Well, I think this is working properly. Oh shit, I have stopped everything, I think. Yes. Okay. I'm going to do it again and that's all. Maybe it's something that it has not worked. Well, and here we have, well, hopefully we could see like this. In our case, we can tip it tomorrow, but well, if I would have to highlight some things over here is the mixed mass scalar from -1 to +1. In the beginning, it was 0, but for now, for Qiskit, it's better -1 and +1. In TensorFlow was better 0 to 1. Another transformation are the standardization, for example, that we have done over here. Maybe if we include that, we could get better ones. But if I go to highlight something, is this transformation of the data to get a really good data to get a good one. And the second one is the PCA, where the PCA, in that case, once you had the PCA with the new columns, is then when you standardize the data. But the PCA, what it does is that it feeds the information to 4 columns, and these 4 columns explain the mostly information of the data set. Okay, this, to be honest, is the parts that I would highlight at most from that. Why? Because in that case, as you can see here, it targets that the rest are something that in that case you cannot see, and you just need to believe me that this is correctly done, etc., because you cannot see the execution. But sorry, this kind of data, when you can see the data set, the table, you are much able to do these kind of things. That is just put me in that the direction, not direction, in that format, in this structure. The y values are those related to this fraud data column. The x value are this one, etc. Okay. Then the mixed mass scaler for the new one with the standardization that I have done above. And the last one is to train the split to have train test and y test. The X data, training data and test data. And then we include this into the classification. As you can see here, the classification was 0 or 1. So in case it's 0, I will put -1 because I wanted to use the upflow formula. And the upflow formula is not classifying between 0 and 1, is only classifying between -1 and +1. And so because of this, I did so. Okay, and well, that's all, more or less. Maybe tomorrow I will try to execute this tomorrow with this, but no, the fraud detection is not. But in case, yeah, let's see whether we have results right here or not. As you can see, the classification is has not been done very good, very properly. Okay, we have the Gaussian dataset, and then we perform some data training, because in that case I have put not false. Okay, I don't remember now what this is. Well, then we do with this ZZ feature bar, the 2 local ansatz for the trainable data. Then we have the observable that it has been done with X and Z. Maybe if we do with Z alone, it's better, as we have done in previous examples. Then we transform the upflow QNN formula, and then we see how is the score like. The training set is 0.56, and the test set is 52. Is to say, shit. Sorry, guys, for the word, but it's a very bad one. Okay, Gaussian is very difficult to assimilate, and as you can see here, there's all surrounded by red are all the labels that has been wrongly corrected. Okay, and the prediction is exactly the same, as you could see, is 0.52 in the test data. In the training data, this is the training data, and this is the test data. Let's see with 2-lawyer QNN, where the 2-lawyer QNN is the Z observable, and as you can see here, the score is exactly the same. Very bad. Okay, very bad. The accuracy is not even 60%. It's very bad. Very bad. Probably I haven't achieved this because the Gaussian data is similar to other pre-processing classical that is need to be done, and it's not the one that has been done in Qiskit, or maybe it's because the model quantum lawyer, it requires an hybrid quantum neural network to develop better executions, and not this one. Now we will use the circuit QNN, and as this is a how can I say that? As this is a circuit QNN and this is a binary classification, maybe it could improve the results. And this is still fitting. So if you want, guys, as it plays Spain right now, we can let that here. I will execute all of this for the class tomorrow, and I will have this. We will see what are the results over here, finish that part, and follow with error mitigation. Do you agree with that part, guys?
Yep.
Yes,
Awesome.
no problem.
Awesome, guys. So I'm going to stop this. Okay. I'm going to stop sharing.